111 Welding. This series of PowerPoint should familiarize you with common equipment and procedures that the FAA will expect you to be able to answer some questions about. So as we move through this, I'm going to point out the important or key factors that you should know. And at the end of these slides, there will be unit questions. You should be able to answer those unit questions. If you can, it's going to make your exam, progressive exam in this material, very straightforward. The FAA questions about welding will be referencing the AC 43.13-1 Bravo. It will accompany the textbook for this course. It contains some very important information that's going to answer several questions on FAA exams. The first thing you should be able to do is define welding using a traditional meaning. Well, welding is simply the process of joining materials together while they're in a liquid state. We apply heat, the base materials turn liquid, they flow together, cool, solidify, therefore creating a strong joint. So there's the first piece of information you'll need. The second point I'd like to make on this PowerPoint is there's a common question is what are the three types of welding? Well, the FAA recognizes these three types. Gas welding, the oldest method, electric arc welding, which is going to be all of your modern methods, and then finally resistance, known to many of us as spot welding. However, spot welding is generally used in a manufacturing environment, not so much in repair, but there's your answer to that question. Another common question is, what are the most common gases used in gas welding? Well, oxyacetylene, oxygen and acetylene are combined for the majority of all gas welding work that will be done. In some cases, they'll use hydrogen as a fuel gas when they're doing aluminum welding because hydrogen contains no carbon and aluminum does not benefit whatsoever from additional carbon being added to it. Now, under electric arc, there's MIG, metallic inert gas, TIG, and multi-arc, which most of us know as stick. In gas welding, the heat is produced by combining two gases, generally oxygen, and in this case, acetylene. It was the first method used to weld with because you needed no electricity. It is important to note, though, that without the addition of oxygen, acetylene will not burn at a temperature high enough to melt metal. So it takes those two gases combined. That's the reason you'll always have an oxygen involved with a fuel gas in gas welding, is to get the temperature high enough to actually weld. Welding, also known as spot welding, is a major manufacturing method. The two electrodes you see in the picture are there to flow a very high amperage current. Because the metal itself provides more resistance to flow than the electrodes do, the byproduct of resistance is heat. And in this case, the current flow heats the material to the point that it reaches that molten state. As soon as the electricity is taken away from this, the metals cool, and guess what? We have met the traditional meaning of welding. We've heated the material until it reaches a molten state, it joins together and cools, solidifies, and creates the weld. Welding is one of the easiest types to do because once the machine is set, you're always going to get the appropriate flow. The material's clamped under pressure. Generally, there's a timer sequence, so as soon as the contacts start to flow, they'll flow amperage for a limited time, then automatically shut off, creating the perfect spot weld. Each of these types of welds have a place in aircraft manufacturing, and the general rule is parts that were welded during manufacture may generally be repaired using the same process. So it would be important for us to understand what process was used in order to create the repair using the same materials and methods. Not all parts that were created with welding can be repaired by welding, but a vast number can. This is a basic list of what could be repaired, typical welded repairs that could be made. Like I said before, there are limitations, but these are some that are commonly repaired listed here. Again, these engine mounts are typically repairable by welding. They were created by a welded method, therefore we can repair them using a welding method, assuming we have the material, the equipment, and knowledge to be able to do it. Parts are repairable by welding if they did not go through some form of a heat treatment, and that's going to be true for all welded parts. If they were welded and bolted on, then they're generally repairable by welding. However, if they were welded, then put through some form of heat treatment, we cannot repair them in the field because we typically do not have access to the heat treating equipment to reestablish the hardness of that part. Example of a structural steel, tubular steel fuselage for an airplane. Once again, this was manufactured through processes. Generally, they don't go through a heat treatment, so therefore we could do field repairs or have someone come in and do a welded repair in that shop. Many of the older aircraft, and believe it or not, now some newly manufactured aircraft also have control surfaces and large portions of the aircraft structure that are made from welding lightweight steel parts together. In this case, control surfaces, this whole empennage has been fabricated from either steel tubing or sheet steel, which makes it eligible for welded repair in the field. Fitting. Now, what I want to point out is that a fitting in welding has a different meaning than a fitting in hardware. When I think fittings, I generally think hydraulic fittings, lines, fittings, parts and pieces, fuel, hydraulic, oil, oxygen. But in welding, a fitting is anything that's welded to create a point that we can attach another structure. So in this picture, you're seeing a welded fitting, and I'm not sure what bolts on here, but it allows attachment through hardware of another steel structure to this original steel structure. Many fuel and oil tanks are repairable by welding. However, it is a very dangerous undertaking to repair a tank, especially something that's held a volatile liquid, because there is the potential that that thing can explode. So in order to weld these, you must be trained in how to purge them and make sure that they're continuously free of vapors before you would ever attempt any type of welding method. Many people have died in this process because of injuries, because what they were welding on had or contained some form of a gas that was flammable, even though they thought they were clear. Most common steel alloys used in aviation is 4130 chrome moly tubing and sheet material. It is a very weldable steel. It's also a very high strength to weight steel, so therefore we can use lighter parts and still achieve the strength required. So typically steel parts manufactured from 4130 chrome moly steel are weldable. This is also an FAA question that comes up. What is the most common alloy of steel used? SAE 4130 would be your answer. So the question may be, why do we choose to weld a joint? Because it takes equipment and skill levels not typically found with every mechanic. Well, here is your list of answers. Rigidity. A welded joint is a very strong joint. Simplicity. Welded joints require less machining, less hole drilling, less time to fabricate. Welded joints can be very low weight. The amount of steel used to make a weld can weigh a lot less than hardware might. It's a very strong method. The welded joint, if it's done properly, is stronger than the material itself, so there's no worry about strength. Economy is a big issue because aircraft hardware has a cost, and the amount of filler material used in welding is generally penny on the dollars compared to the cost of hardware to create a joint. And then finally, the speed of fabrication. A good welder can weld that joint and many, many more like it in the time it would take to properly drill and attach with hardware. So there's your list of why we still have welded parts in aircraft. About when we could weld or would weld, it's also important to know when we shouldn't. Knowing when not to do a thing is a very important piece of knowledge. And many of these parts, because of the strength requirement, were welded and then hardened or strengthened by putting them through a heat treating process. Certain materials also are put through heat treating processes that make them undesirable to weld because we destroy the characteristic that made them eligible to be used in aircraft. As a rule, if it has gone through a heat treating process prior to being welded or after being welded, that's not something we can approach and repair in the field because it's going to require ovens and control processes we don't have access to. Now, any material, this is another rule, it's very important to know, if it was a previously soldered or brazed joint, it is not eligible to be welded. We will speak more about brazing and soldering. It is not a welding process, and it creates a circumstance to where a weld will never be reliable if we try to go behind them to create a repair. Now, we're going to begin a list of what not to weld. And here's your listing. Oleo struts, generally they go through a plating and hardening process. Therefore, if we weld, we'll destroy the plating, we'll destroy the strength properties through heat treatment. We never weld any engine part. It is completely forbidden. We would never perform welds on any type of hydraulic cylinder valves, fluid lines, fittings. If it's hydraulic, most of those parts have gone through a heat treating process. We'll just destroy their property. We could never weld on any portion of a propeller. As a matter of fact, mechanics are strictly limited to what we can do, even under normal maintenance to propellers. And any type of aluminum skin or former are not eligible to be repaired by a welding process. Majority of material used, aluminum sheet, in structural applications have gone through a heat treatment process. If we weld that material, we'll destroy its strength. So, good list of things not to weld. In a couple of pictures. This is simply things on the previous list. You can see them and sort of identify with them. No internal engine part, or external part for that matter, is eligible for a welded repair in the field. At times, engine parts are welded as a part of a remanufacturing process, but that can only be done at FAA approved repair stations in which they have the authority and they've been inspected and proving their ability to do the thing. Propellers in general are one of the most high stress parts found on any aircraft. Because of these stresses, and there's 6 or 7 acting on a prop at once, we're simply not allowed to do a welded repair. Once again, if it is repaired through welding, it would have to be done at an FAA approved repair station where they have the methods and the inspection techniques to return that part. It is not legal for a mechanic to do that. The most commonly used alloy of aluminum in structures for aircraft is 2024 T3. The T indicates that it has gone through some form of heat treatment. The 3 indicates what kind. So because it has gone through a heat treatment, a weld will destroy that aluminum's strength and rigidity property. Therefore, it is not acceptable to weld on any structural aluminum part. Cables, cable fittings, it is not acceptable to weld. Once again, most aircraft cables are made of steels that have gone through a heat treatment. Therefore, if we weld them, we will destroy their strength properties. Also, once again, just to reiterate, brazed and soldered joints, it is never acceptable to weld behind those methods. If they were made by soldering or brazing, they must be repaired by the same methods, same techniques and materials. No aircraft hardware should ever be welded. If you look at the bolt on the left, that gold color is a plating that's put over the steel to protect it from corrosion. Any weld would destroy the plating, and aircraft hardware has all gone through some form of a heat treating process. So if we do attempt to weld, we're going to destroy the strength properties, and we will destroy the protective coating put on the hardware to help it survive in a corrosive environment. Therefore, no welded repairs on any hardware. Now let's begin the discussion about welding equipment. There's some common questions that need to be known in order to understand the equipment and test well on it. To start with, we'll look at an oxygen cylinder. The cylinder itself is designed to hold generally up to close to 2200 psi or higher of pressure. Therefore, the cylinders are manufactured with seamless steel, and they make these cylinders in several sizes. Generally, the size is based upon how many cubic feet of gas it'll hold. Now, for oxygen, there's a universal standard that all oxygen bottles are painted green for identification. Green is your common color. On each gas cylinder, you will have a valve that allows the companies to refill the cylinders when the gas is low, and it allows us to open the cylinder to use the gases. The key thing about an oxygen cylinder, as you can see illustrated on the right-hand picture, is that there's some safety built into these valves that go on the end of these cylinders. To start with, these valves are made of brass. The reason brass is used is brass will not create a spark if it's hit by other types of metals. So it's spark resistant, making it safer. Now that does leave the valves being softer than many other metals. So therefore we have to be careful when the safety cap is off the cylinder, because it's conceivable that we could break a valve off, turning that oxygen cylinder into an unguided missile. Another safety feature built in is there's a burst disc located opposite of your supply side. If the bottle were to be overheated, that bursting disc would melt and allow the oxygen to discharge from the bottle before the bottle exploded, turning into shrapnel. So let's review really quick. Oxygen is green. It's in a cylinder that's made of seamless steel. It'll have a brass valve installed in it. And in that valve, there's a disc that's always open to the bottle to allow pressure to discharge in case that disc melts or the pressure overcomes the disc's structure. That allows the bottles to dump excess pressure, keeping the bottle safe and keeping it whole. This is a little better illustration of that particular circuit in that bottle. Generally, these discs would melt at around 240 degrees Fahrenheit. Once it melts, the oxygen can discharge at a reasonable rate, lowering the internal pressure of the bottle, keeping it safe. An oxygen bottle that explodes is simply a bomb, and the fragments of steel will penetrate through block walls. So this is a much safer way to manage these bottles in case they're overheated and overpressure. Slides. All oxygen equipment uses right-handed threads. By that, everything tightens to the right, which is common in our hardware world. Also, if you move an oxygen bottle, even if it's across the shop area, you should always put your safety cap on before the bottle gets transported. If the bottle were to fall over and knock that brass valve off, it could penetrate through several walls of the building before the pressure drops enough that the bottle slows down. Like I said earlier, they become an unguided missile. I'm sure you can find many, many videos on YouTube of the end result. So 2 key points: right-handed hardware on oxygen equipment, and the safety cap must be screwed in place before moving the bottle in order to keep the transport safe. Time you're handling oxygen, whether it's welding oxygen, aviators breathing oxygen, you should only use clean tools, free of oil or grease. The reason is oxygen itself does not burn, but it makes any fuel that it comes in contact with very susceptible to just ignite. Because of that, all tools, equipment, even our hands and clothes should be free of grease and oil. When we are dealing with servicing or changing out oxygen equipment, you should never use anything petroleum-based to check for leaks or to lubricate threads. In the older days, beeswax was used. Now there's synthetic compounds we can use for leak checking, also for thread lubrication. Anything else that comes in contact could very easily spontaneously ignite, and it'll burn extremely hot and extremely rapid. Acetylene cylinders, they're similar to oxygen in a lot of ways, but there are differences because acetylene gas is a very different creature than oxygen. Once again, they're a seamless shell, but they weld the ends on, and the reason they're allowed to do that is because acetylene bottles will always be a lower pressure bottle than oxygen bottles. Bottles, unlike oxygen, which are hollow bottles, are actually filled with a porous material similar to a very lightweight and porous concrete, cement. Now, also, they are filled to about 40% of their volume, not quite half, with liquid acetone. Acetone is typically a solvent and a cleaner, but in this case, it serves a much more important role. Acetone absorbs acetylene gas. It is very important that we stabilize acetylene, and the best way to do that is to take it from a gaseous form and soak it into a liquid. It is much more stable in that liquid form and much safer to use that way. The porous material stops the liquid from being able to splosh in the bottle. It would be much like buying a new Coke and shaking it. As soon as you open it, you're going to spray Coke everywhere. Well, the acetylene bottle's porous interior stops a lot of fluid movement, which keeps the fluid calm and keeps the gas suspended in the liquid solution. Itself is not found in the atmosphere. It's a manufactured gas, and they do it by combining water and calcium carbide. When we go to the lab, you will smell the acetylene. It's got a strong odor. The acetone and the absorbed acetylene can be pressurized. Acetylene by itself becomes extremely unstable above roughly 15 psi, and it will explode without an ignition source at approximately 26 psi. So as you can see, if we're going to take acetylene gas and pressurize to 250 psi, we have to stabilize it, and that's the purpose of the acetone. By absorbing it into that liquid, we can then pressurize the gas to a high enough level to make it useful for us with welding equipment. Acetylene cylinders have a safety on them, similar to oxygen, But with oxygen, you have a bursting disc located in the valve on the end of the bottle. Acetylene bottles actually have a fuse plug, or what could be referred to as a thermal blowout plug, that screws into the body of the bottle. Well, once it threads in, if the temperature gets high enough, the plug will melt, allowing the gas to escape the bottle before it reaches the point that the bottle explodes like a bomb. Plug or blowout plug typically will melt somewhere between 212 and 220 degrees. It allows the gas to escape and burn rather than explode the cylinder. This slide is that because acetylene is suspended in a liquid, you should never lie an acetylene bottle down to use the gas. You will end up burning the liquid out of the bottle, which will consume about 25 times more acetylene than is needed. Well, in the end, you will use up acetylene very quickly, and the cost to replace it is fairly expensive. So all acetylene bottles should only be used while standing up. Many times bottles have been laid down in equipment in order to transport. That is fine. Just make sure you stand it up before you start using it. All acetylene fittings, hoses, equipment has left-handed threads. That's a key point. Left-handed threads are utilized on acetylene equipment. Therefore, oxygen and acetylene equipment could never be hooked up in reverse, which could create a very dangerous circumstance. Also, acetylene cylinders are painted a distinctive color, and black and orange are common colors. I have seen them other colors, but one thing is they'll never be red. Red is not used in cylinder gases because it is reserved for emergency fire equipment only. You would not want to accidentally open an acetylene valve to put a fire out. I assure you it would not work. So therefore, fire equipment is red. Cylinder gases will be painted other distinctive colors. Look at a piece of equipment that's very important, and there's some FAA questions involving this equipment. We have to get the high pressure gases down to a pressure that we can work with. And the way we do that is by the use of pressure regulators. In this case, this is what we would refer to as a dual stage regulator. And the way I know it's dual stage is we have two gauges visible on the regulator. Now here's a key point. The gauge nearest the bottle will give you your bottle pressure. The gauge furthest from the bottle and closest to your torch connection reads our working pressure. With these type of regulators, we've got at-a-glance information. Our working pressure may vary based on the equipment that we attach to the hoses. So we'll have a work pressure gauge, then we'll have a bottle gauge. Once again, these regulators are made primarily of brass because brass doesn't spark. And you turn the knob on the regulator in to increase pressure, out to decrease. There's a video that accompanies this PowerPoint in the module further explaining this. But this is a dual stage regulator because it has two gauges. The gauge closest to the bottle is your high pressure gauge. The gauge furthest away, closest to your hose connection, is your low pressure or work pressure gauge. We can set the work pressure by turning the handle in and out on the regulator for the desired PSI. Lab, you won't see dual stage regulators at each work location. And the reason is we have a manifold system. We'll set our main pressures outside, then inside we will have a single stage regulator where we just adjust our work pressure. Once again, it's obvious that this is a single stage regulator because there's only one gauge on it. When it only has one gauge, that's our work pressure gauge. There are some maximums for our gas pressures, for our working gas pressures. Acetylene, we try to limit to no higher than 15 psi. Above 15 psi, acetylene becomes unstable. Oxygen's generally limited to 40 psi. As per the norm, we would always go back, look at our manufacturer's information for our torch equipment, and we would set up accordingly. Typically, as you change tip sizes on welding torches, you would need to adjust your pressure to accommodate each tip size. Things that can happen when using a torch. One is dangerous, one is common. A flashback is a dangerous circumstance in which the flame goes out, or you think it does, from the exterior of the torch, but it actually starts burning back through the tip, through the torch body, and into the hoses. When that occurs, you won't see a flame, but because the flame's burning inside, there'll be smoke coming from the tip, and you can feel some vibration in the torch body itself. If the flame's allowed to enter the regulator, there's a possibility that it could enter the cylinder and cause a great explosion. It's dangerous. However, flashback arresters are used. It prevents the reverse burning of those gases into that system. All of our equipment has flashback arresters installed. However, make sure you contact me if you feel that a flashback has occurred. Your equipment and you think you're experiencing a flashback, turn the main valves off. Come immediately to me in the lab and let me know. The flashback arresters are there to prevent a dangerous situation from occurring, but I want to be made aware because I change those arresters if I feel like that's occurred. It's not necessarily required, but they're not very expensive, and it is a good step toward keeping the lab safe. Image of common flashback arresters. They're an inline device. Generally, they're attached to the regulator, then your hose is attached to them. Therefore, the flashback could never get into the regulator or the gas supply lines feeding your torch station. That is a common occurrence is called a backfire. Although it is a little bit disconcerting when it first happens, it is not a dangerous event. It's a momentary backwards flow that'll pop and come back out of the tip, and generally is caused by a few mishandling problems, like a dirty or stopped up tip if you're trying to run the wrong gas pressure for your tip size. If your tip is loose in the torch body, or if you hold your tip too close to the workpiece and overheat the tip, that can sometimes cause a backfire. Also, if you dip your tip down into the molten metal puddle of the weld, that can cause a backfire. Now, a backfire is not dangerous. However, if it backfires because you touch your tip, it could push some of that molten metal out and cause it to burn holes in clothes. So therefore, don't wear clothes into a lab, into this lab specifically, if you're not willing to get a little bit of damage. Good clothes can get ruined in that process. Oxygen equipment has right hand or common threads. It's the same threads we would use in hardware. Left-hand threads are kind of uncommon. So all of your oxygen equipment, to put it simply, is righty-tighty, lefty-loosey. Type of torch, and the type that we'll use is known as the balanced pressure. It uses equal oxygen and acetylene pressures. It's a lot easier to control the mixture, and it's commonly found. Injector types are generally not used in aircraft welding or in common gas welding. Itself is essentially there to provide hose connections to provide a place to install the welding tip, and it also contains the valves that let you control gas flow. These valves are precision valves, they're needle valves, and I will say this, they require very slight pressure to turn on and off. Most people tighten too hard, which could lead to damage of these precision valves. Remember, when you're turning a torch off, light pressure on the torch valves is sufficient. Any more than that is creating unnecessary wear and tear. I said before, your torch body provides a place to connect your welding tips. Tip sizes change based on the thickness of the material that you're welding, and the torch body also provides a place for the hoses to connect. The green hose will always be your oxygen, the maroon hose will always be your fuel gas, and the torch handle itself is cooled because the gases flowing from the valves are mixed within that torch body, providing something cool to hold on to while at the same time mixing the gases internally to get a much more even burn. The tip is there just to deliver the mixed gases to create the temperature. This is a very common FAA question, and it's often missed. Here's the point I want to make to you. The opening in that tip determines its size, and the tip size determines how much gas can be burned. Therefore, tip size determines the amount of heat produced. Heat is measured in British thermal units, or BTUs. The tip size does not control the temperature of the flame. And here's one way I've learned to explain this. If I take a birch tree and I cut it down and I set the log on fire, the entire log, it's going to burn at a temperature, and it's also going to produce a certain amount of heat. If I take that same birch tree and I make match stems out of it, and I were to ignite a match stem, guess what? The flame that match stem burns at is the exact same temperature of the flame the entire log burns at. However, a matchstick would not heat a room. However, a log in the fireplace could. So therefore, tip size determines the amount of heat, not the temperature of the flame itself. Keep that in mind, and when you see that question, you'll learn the points. Sizes are assigned by the manufacturer. However, not all manufacturers run the exact same holes for the number they assign. So, depending on the manufacturer, you would select a tip number, which determines the hole size, and you would select that based on the metal thickness. The thicker the material, the more heat is needed to get it into a melted state. So therefore, we go up hole sizes for thick material, we go down hole sizes for thin material. Each manufacturer sets that. Unfortunately, they don't all match. However, they all produce a chart that allows us to select the right tip size based on the metal thickness that we're working with. That makes life a little bit easier. As stated before, the tip size determines the temperature, not the temperature, the heat output, which matches material thickness. There's also a couple of terms dealing with flame that needs to be understood. There are soft flames, medium flames, and harsh flames. When you're describing a flame using those terms, what you're actually talking about is how much gas pressure is being used to create the flame. So a soft flame has a low pressure coming to the tip, medium, and then harsh is because we're using higher and higher pressures as we go along. This is a key thing in creating flames because each tip size works within a range. If we want the low range, often we're going to run lower pressures. If we want more heat produced, we'll have to flow higher pressures, burn more gas to produce more heat. However, each tip size has a limit. if I try to flow too much gas out of too small of a tip, it'll cause the flame to be harsh. And on a lot of materials, they won't tolerate a harsh flame. So we like to use soft flames for aluminum and medium pressure flames for steel. I can't really think of a good purpose for a harsh flame other than if you're just possibly trying to heat something up quickly and you don't have the right size tip to do the job. Keep that in mind as we move forward. The right tip size, the right pressure creates the right flame type to work with. Now let's take a look at three different flame types. These feature prominently in FAA questions, and also you'll be required to make three different types of flame when using the torch to pass your practical. The first one is what we refer to as a neutral flame. It's a 50-50 mix of oxygen and acetylene, and when you're at that right mixture point, the flame actually creates certain characteristics that you can easily see. We're going to take a look at these flame types as we move along. The neutral flame will have two parts. You'll have an inner cone, the smaller blue flame that you see in the drawing. Then you'll have an outer envelope, but they'll be distinct. There'll be two parts. And as we move through, we'll discuss the characteristics of the other types of flame. Plus, we'll cover this in the lab. Majority of welding, soldering, and brazing, if done with gas, will be done with a neutral flame, that 50-50 oxygen and acetylene type. Another type of flame that you'll be required to make and recognize is a reducing or commonly called carburizing flame. In a carburizing flame, we're actually burning more acetylene than oxygen. And the free acetylene or the free carbon is given off. Basically, we're not burning hot as a neutral flame, so the extra carbon provided by the acetylene will get put into the work that you're doing. It'll be absorbed into the surface of the steel or stainless steel. If too much carbon is used, it can harden the steel to the point that it'll cause it to crack. There are places where a reducing or carburizing flame is desirable. Some stainless steels like a little extra carbon to help them restore that stainless property or anti-corrosion property. Welding them reduces that by adding a little additional carbon back. It helps the material regain that particular characteristic, but it's not often used outside of those particular uses. The final type of flame that we'll look at will be the oxidizing flame. Remember, the three types are neutral, carburizing, and then finally we're looking at oxidizing. If it's an oxidizing flame, we're burning more oxygen than we are the fuel gas, in this case, acetylene. Now, it creates a harsh hissing sound. You'll hear the flame, as the flame changes, you'll hear a change in the torch. It'll become harsh, the colors will become pale, and you'll start hearing an underlying hissing sound. Now, the inner cone, that blue initial flame, gets pointed, it gets pale in color and harsh as we create this type of flame. There are a few instances where we want an oxidizing flame. Some types of solder require a very clean flame with no excess carbon being introduced, but it's very limited. Once again, the neutral flame is our most common type used across most methods of welding or brazing. Visiting what these flames look like. Remember, a neutral flame is going to be burning oxygen and acetylene at an equal rate. You'll only have two parts to that flame. And if you'll look at this drawing, you'll note that the first small flame coming out of the torch tip has a soft round end. It's darker in color. And then we'll have that second outer envelope flame. If you're running a neutral flame, your torch will be quiet. It'll be burning clean. And that's exactly what we're looking for. For some reason, and it happens occasionally, you'll have a tip that'll pop because it's too close to the work. And sometimes that melted metal will come up at the edge of the tip. It'll cause the flame to distort and split. Well, the process is we would need to clean that tip. There are tip cleaners, as you see here, all over that lab. And what you do is you start with the largest cleaner that will fit in that area and gently move it in and out. They've got serrated edges, and they'll grab and clean the particles out of that tip. If you have a split flame, it's a dirty or damaged tip. The first step we're going to do is grab these tip cleaners and clean the orifice out so that we get a smooth, properly shaped flame. Covered in our safety brief, we'll only ignite these torches using strikers. They're designed to do the job. They're the safest way to do it. We would never use match, butane lighters, propane torches. We always start with a striker. It's the safest and the only approved method. We'll use approved welding goggles. Remember, shade 5 lens is good enough for gas welding. It's not as bright as other methods, but we must have goggles. They do a few things. They protect your eyes from some harsh light that's created. They keep the heat out, and they keep splatter and other debris from getting in your eyes. Do not come to the lab and start melting metal without an approved set of goggles, and sunglasses will not do, right? Costas are not safety approved necessarily. This in our safety brief, but you must have gloves in this lab. A standard pair of cloth or leather work gloves will do fine. Make sure you get those before our lab day. I'm not guaranteed to have enough equipment to spread around. You're supposed to have these. Besides, a good pair of work gloves is good to have with you anyway. Slides briefly with you, but in general, there's 4 types of welding we can do: flat, horizontal, vertical, and overhead. We'll see them in these next slides. That you're above it, you're making it on a tabletop, bench, or in place. Probably the easiest of all the welds to make, certainly my favorite. Not going to be flat. We're going to be making a weld that's on vertical, but we're going to be welding across it horizontally. A little more skill and a little more difficulty in this type of weld. Has more complexity. Out of all of them, this one's probably going to require a little more skill to make. It's also called welding uphill, and it takes a lot of practice. But if it's on the aircraft, we never know which direction we're going to have to weld, so you'd have to be skilled in all of these welding positions. The overhead weld, my least favorite, because everything's taking place above you, and anything that falls from this type of welding is going to fall right on top of you. Therefore, your gear and equipment must be correct to keep you from being burned. So, through several different types of joining of this material. So I'm going to put some emphasis on the FAA questions. A butt joint and a T-joint are the ones that the FAA asked the most questions about. So we're going to look at these together. Simply joining edge to edge material. As you can see by this drawing, it's a very straightforward, very simple setup. Another very common joint used in aviation and across many other industries. There's going to be some questions about these two, and we'll cover these shortly. Joint, don't see it as often On occasion, we'll see it, but butts and T's are the most common. Don't come up all that often, but you do see them on fuel tanks and tanks of different types. Always enjoyed these because you had a chance to try to make a very beautiful edge and a cool bead. We can just have you take a look at an edge joint. Not as common, but this is a good example of what an edge joint would be. We weld something, we're going to have to induce a tremendous amount of heat into it, and all materials. This is a common FAA question dealing with physics, and the question is, what types of matter are affected by thermal expansion? Well, all types are, but when we're dealing with welding, that expansion can create some difficulty for us. As we add heat, the material will expand. That's known as the coefficient of linear expansion, and it's shortened to K, the letter K. And because of this, and this principle that the material that we're going to work with is going to continuously grow while we're working with it, we have to look ahead to prevent some problems. We don't make allowances or take steps before we weld material. Because of the linear expansion, we could end up with our materials warping, buckling, or losing our desired gap between our metals. So because of this, we're going to use some methods to counteract this linear expansion or K factor. One method or approach, not my favorite, is the tapering space. If you could imagine starting welding on the right-hand side of these two coupons, as we weld, the heat is going to cause them to expand. So the crack will continuously close as you're welding along. The only problem with a tapering space is you have to correctly anticipate how much gap to put at the end. I've never been great at that, but it is one method to compensate. These are procedures that we can undertake in order to control this expansion to help prevent the warping or buckling of the material. And one is to preheat the materials we're going to weld. If we preheat them, they expand and stabilize, making them much more predictable. Another method is to put objects near where the weld's being made to pull the heat away from our welded joints. Those things are called chill bars. Generally, copper's the best, but it could be made of other materials. My personal favorite is the last one. We simply tack weld the joint to firmly hold it in position while we're making the weld. And that's also the FAA answer to one of its questions, is how do you control expansion when welding a long joint? We're going to tack weld at intervals. That'll answer that question, and it's also my favorite choice to control warping and buckling. We simply tack periodically. Now this works great on thin materials. On thicker materials, we often have to go and take a little extra time. But for most aviation welds, you're going to be dealing with thin materials, and tack welds are sufficient. What goes up must come down. Well, in this case, whatever expands because of heat will also contract as the heat leaves the part. Contraction is simply the shrinking of the metal as it's cooling. And if you're not careful with expansion and contraction, it could cause cracks in the area of the weld. So preheating material, welding at a slow rate, controlling the cool down, that's a really big deal. We need to control the cool down, can reduce the effects of contraction dimensionally, and it reduces the effects of contraction, which could cause cracks. You say, well, how do you control your cool down? We bring the heat away from the part slowly rather than rapidly. Simple illustrations that give you kind of a feel for what's happening during the expansion phase, what's happening during the contraction phase. The methods you use help control this. This is what we've been saying. If we preheat before, tack before, while we're making our weld, we'll have more control over expansion. Then, after we're done with that weld, we're going to take the torch away slowly, control how quickly it shrinks, and we can eliminate a lot of this warping and buckling. Also, I will say this, there's times that despite your best effort, you're still going to have some movement after a weld is made. It's going to be undesirable. It doesn't mean the piece is bad. There are some things that we can do to step back in and help straighten that part. In this case, to save the part, we can reheat the entire joint nice and even, not melting point, but elevate its temperature. And then we're going to allow it to slowly cool back down. That'll release the stresses in the material. It'll also help us bring our material dimensions back to a more desirable, well, straightness or whatever the characteristic that we're looking for. When we reheat and allow them to cool slowly, that term is known as normalizing. And normalizing removes the stress of a weld. Normalizing often can help straighten a part that's warped. That had heat treatment applied after the weld is installed on the aircraft, we can't repair it. However, FAA approved welding repair stations can. They'll take that part in, make the weld, then they'll put them back through the heat treatment process. Initially, that's going to normalize the part, then it'll return to the original hardness. I can't see into the future and say you will or won't work at one of these places, but I can say this. If it's a heat-treated weld, then it's going to have to go to one of those places to be made. So how does that affect us as the mechanic on the scene? Well, that simply means we take the part off, we ship it to that repair station. They do the repairs, they do the paperwork to make it airworthy, then they ship it back and we reinstall it. Discuss filler rods a little bit. Why do we need a filler rod? A good weld, if you look at the required dimensions, will be thicker than the material that's joining it. So where are we going to get this extra material from to make the weld thicker than the base material? Well, that's going to come from some sort of filler. In gas welding, we use filler rods. The biggest key factor and the biggest question that comes about filler rods is, what's the most important characteristic when selecting a filler rod? Well, the most important is it must be compatible with the base material that we're welding. If it's not compatible with the base material, your weld will be corrupt, it'll be a bad weld and a weak weld, so everything else won't matter. And if the part does have to be heat treated after the weld, the filler material must also be of a type that'll accept that heat treatment and harden along with the part. Now, mild steel, what we refer to as a mild steel filler rod, are most commonly used with 4130, and that's the most commonly used alloy. So they're not necessarily, the majority of work being done with filler rods are being done with mild steel, pretty common, pretty straightforward stuff. With some types of rods, we have ferrous and non-ferrous. This also comes up on FAA questions. What is a ferrous material? Well, a ferrous material is simply a material that contains some iron. Iron's atomic symbol is Fe. You can see it right there in the beginning of the word. And ferrous materials also have a magnetic property. So a magnet can stick to it if it is ferrous. Non-ferrous down here, no iron content, is stuff like brass, aluminum, magnesium, copper, silver. There's a lot of metals that have no iron in them. They're considered non-ferrous. Anything titanium iron is considered ferrous. 4130 is certainly a ferrous material. Mild steel is a ferrous material. Rods typically come in packs, sold by weight, and most of them, like I said, will be mild steel rods. But when you look at them, they have a shiny copper, bright copper looking finish. And that is simply because they are indeed coated with copper. Mild steel will rust. Well, rust is oxide. If it goes into our weld, it'll corrupt our weld. So the way they protect the filler rods is they flash a very thin coating of copper on top of the mild steel. What this does is keeps the atmosphere from getting to the steel filler rod material. And if no atmosphere can get to it, it can't rust and ruin the rod and corrupt the weld. Now, these filler rods come in different sizes, from 1/16 on up to much bigger around than that. These diameters vary, and there's a simple rule. Match your filler rod thickness with the material thickness of the weld you're going to make. So once I know my material thickness, I can select the right rod. And the question may come up, well, what happens if I take too small of a rod? Well, you're going to have to feed it very, very quickly to try to build enough filler up. B, it's going to overheat. When it overheats, it burns the weld. Your weld is too hot. It sinks in too deep. It has a rough and irregular finish on it. It's a bad weld. If I choose a rod too big for the workpiece, the moment I touch it to the puddle, it'll zap the heat out of the puddle, soak it into the rod, and just stick the rod. It's very difficult to keep a puddle flowing if we go with too big of a rod. So what do we need in this case? The Goldilocks filler rod, the one that matches the material. It'll flow, it won't burn up, and you'll make a good, healthy weld. Rods generally come in roughly 3-foot sections. And to try to hold and control a 3-foot long rod is difficult. It would be like writing with a 3-foot long pencil. So what we'll typically do is cut them in half. It helps us control. And as the pieces melt shorter, it gets too hot to hold on to. So we'll lay that one down, pick up another, weld with it, and when we have several short pieces, we can then join them together with heat, create a new rod to work with. That way we're using the material efficiently, and that is perfectly acceptable. First things, after lighting the torch, establishing the proper flames, and shutting down proper, the first step to actually learning how to weld doesn't involve filler rods or joints. It simply involves controlling a puddle of melted steel. So if I assign you this project, if we have time, what we're going to do is take some soapstone and draw some marks on material. You're going to set your torch, and we're going to try to create a puddle and push it along that line until you can control the puddle. You cannot weld. No matter what method you're trying to learn, control of the puddle is the key to all welding methods that we're going to be doing by hand. So that's our first step. Once you've got good control, we can add complexity and you get closer to actually welding in the proper sense. Is put in here just to give you some names for the parts of the weld. I won't cover every one of them. You can hit pause and take a look, but you should become familiar with the different parts and the different names for the parts of a weld bead, because that's going to help you understand what's a good weld, what's a bad weld in discussion later. Might not be a bad idea to kind of sketch this out and label it from memory, see how far you can go. Really big question for the FAA. I see it quite a bit in welding, but it's going to ask you what's the characteristic of a good weld on a butt joint, where we're just going to bring two pieces of metal together. Well, to start with, the penetration should be 100% of the metal thickness. And as you can see by this illustration, the weld in the darker color is not only the same thickness of the material, but it actually rises above the material. That's why we need the filler rods to put some extra metal there. And if you'll notice, it's 3 to 5T. Well, T stands for thickness of the material. So if we're running 1/8 inch thickness material, our weld bead should be at least 3/8 of an inch wide. Should be 100% penetration. And the way you get that is by establishing a gap between those two parts and melting the filler all the way down to the bottom between those parts, then build back to the top side slightly above surface level. That's the way a good joint's made, and that's the way to answer that FAA question. Quite a few FAA questions that may pop up asking you how to deal with different types of damage doing welded repairs. Well, one of the most complex types of welded repairs is when we get a dent or damage where there is a cluster of tubes coming together. Based on this illustration, you can see we've got 4 different tubes that are all coming together in one spot, and we have damage. Most tube repairs are done by cutting out the damaged tubing. But as you can see here, if we cut this out, we're going to cut actually 4 tubes loose all at once. It is acceptable, and the right answer to the question, and this is the question, what can be done at a dented steel tube cluster joint? Well, we can weld on a repair patch, or old timers call them finger patches. We actually reinforce over the existing tubes with a steel patch that reestablishes the strength and reduces the complexity of that welded repair. Question asked, question answered. Questions you would have to ask yourself. Do I have the knowledge? Do I have welding skill? Do I have welding equipment readily available? In other words, am I set up to do this job? Could I weld aluminum? Could I weld stainless steel? Could I weld other exotic metals? And if your answer is no, and most people would say no, then don't weld the part. You would simply order a replacement, or we would bring someone else in that has the knowledge, the skill, and the ability to do that work. I asked this question quite a bit in the class. What if you got a friend that's a professional welder, but he's welding powerhouses? He comes home, you say, hey, could you make this repair? Is that legal? Yes, it is. As long as the weld meets all of the requirements, someone does not have to be a certified aircraft welder to make the repair, but keep this in mind. If you're the mechanic that's signing the work off, you are taking responsibility for that repair, even though you didn't make it. So many times, if the mechanic's unable, we'll bring someone in that can, but the mechanic's still responsible to make sure they're using the right material, they're using the right data, and they're making the proper weld. That's what this class is designed to do, to teach you to be a good inspector, not a good welder. Comes up often. What if the repair that we're going to do, the welded repair, becomes or falls under the category of major repair? When we add the word major in front of repair or alteration, that means that a FAA Form 337 must be completed. Now, who's responsible to complete that form? The mechanic doing the job. Who has the authority to approve for return to service the work done on that form? Well, you must be a certificated mechanic with an inspection authorization. Now, we'll talk a little bit more about this in class, but long and short of it, if it's a major repair, we're going to be dealing with data. We're going to be dealing with an IA in most cases, and responsibilities there. In general, two types of data that could be used to make a major repair and to fill out that Form 337. The first type is approved data. That's data that the FAA has already looked at and approved to use for that type of repair. That could be in the repair manual of the aircraft. It could be a previous Form 337 to make that exact same type of repair. It could be drawings that the manufacturer has sent out in the form of service letters or service bulletins, or it could be contained in an AD that the FAA has previously issued for that repair. All of those things fall under a category of approved data. Now, the other type of data that we're going to look at is acceptable. Hear me when I say this. You never move forward with a repair unless you're working with approved data, previously approved data. Acceptable data has yet to be approved. We do not have permission yet. We're just using something that is generally found to be acceptable, but acceptable data, we're going to be asking permission to use it. Approved data, we already have permission in our hand. Of one of those types of data, this is approved because this data was embedded in an airworthiness directive that the FAA itself issued. Because they issued it, they've already determined that it is good to use, so you're not necessarily seeking permission at this point. You're using information they've given you to move forward with. The question becomes, how does acceptable data differ? Well, acceptable data is generally good ideas. Typically, the 4313 is a good source for that. Acceptable means it's a good practice, but it's not data that's been approved or okayed for your specific need on that specific airplane. So what we could use is the 4313 as a basis to ask permission. We would propose how we would fix it using that. Then we would send it to our local FSDO or Flight Standards District Office to get FAA approval. Once they approve it, they'll send it back to us, then we move forward. Now, never start the work before you have approval, because you may end up with an unairworthy repair because they didn't approve the data and you've already done all this work. On this slide, because we've already talked about you could form a finger patch or steel patch for a dent at a cluster joint. When you select materials to make the repair, the importance on this slide is it must be of the same material, the same thickness. It must fit, conform. In other words, it's the standard rule. Our repair should leave that damaged area at the original or properly altered strength before the damage took place. Well, the only way we can guarantee to put something back equal to what was there is to use materials that were equal to the original.